So if I do this, let me draw a piston cylinder here. And then we'll be down here, bottom dead center of a PV diagram. And so we'll start at state 1, and we'll start at state 1 and we'll have constant temperature heat addition. So 1 to 2 is Q in at T hot, right? So we're going to have constant temperature heat in. Then from 2 to 3, we're going to store heat in a regenerator. So we're going to have a regenerator, and so when I look at a regenerator, I'm going to have something here, and basically I'm going to store energy in the regenerator. So I need to have time, so I've expanded here, and now I'm cooling down this, so where is the energy going? So this is Q regen. So it's like, all right, it's here, I need to have the heat go out in the regenerator, I'm then going to stick it back in later on. So now I've lowered the temperature to state 3, and we're going to have compression to state 4, and we're going to have Q out at TC at a low temperature, and then I'm going to take the heat from the regenerator, and so I'm going to have Q in, Q regen, and now I'm going to take it, and the energy that I took out here and stored, I'm putting back in. And if I look at the TS diagram for this, so we'll look at both. We'll look at the TS diagram for this. You have 1 to 2. 2 to 3, 3 to 4, 4 to 1. And basically, this area here, and this area here, these areas are supposed to be the same, so you can see the accuracy of my sketching in that they don't quite look the same, but the areas, the crossed areas are the same. And this is my Q regen. And remember that on a TS diagram, the heat's the area under the curve. And so the advantage of this is that it has the thermal efficiency of a Carnot engine. So the thermal efficiency of the Stirling equals the thermal efficiency of the Carnot. So you have it equal to W net over Qn is equal to 1 minus Tc over Th. So this is just like in chapter 7 with the Carnot engine, we have that. Actual Stirling cycle engines are not this easy, they're a little more complicated. A big advantage is they can use external combustion. So, practical advantage. So I can use external combustion, so I could burn wood or biomass or whatever I want as a heat source. I could use solar energy as a heat source. So I could use a whole variety of things for the heat source going into this, because the combustion occurs outside the engine, not within it. And now what I'd like, so this is about the Stirling cycle. Just so you have an idea of this, there's something called the Ericsson cycle, which is slightly different than this, but it's the same idea. Now I wanted to look at turbocharging and how that works. And what we're going to do following this is that some people with their individual senior designs, want to turbocharge a car, supercharge a car. How does that work? How do we create a model for that so that we can predict ahead of time what the car's performance will be?